Okay, so this is the demonstration portion of Lab 1 for Machines 2. Right now I'm kind of showing you an image of the DC drive that we're going to use. We're going to use that just for the armature control because we need different values of field current and field voltage, and this is a set field, and so I can't vary it. Okay, so we're just using this for the armature voltage. Okay, and what I'll do is I'll show you some of the other instrumentation here, right? So if you haven't been here before, we have field voltage and current meters, and armature voltage, armature current. Okay, and then this is our DC motor here, and it's coupled to an AC motor on the other side. So right now what I'm doing, I'll show you some of the rest of the setup, right? I have a variac, a bridge, and an ammeter over here. And what we're going to do with that later in the lab, we're going to use this to produce a braking force for the DC motor, right? So you apply DC voltage to two of the phase connections of the AC motor, and that'll create a brake. So we can do some load testing of the DC motor as well. Okay, and then if we come back over here, I've got a bridge and a variac over here, and what we're gonna do for that is that's for our field voltage. Okay, so for the first portion of this lab, what we have to do is do the blocked rotor test to find out what the armature resistance is. Okay, so I'm going to do the readings here. What you're supposed to do is take the current up to the rated current, and these DC machines are rated at 5.2 amps. So I'm a little leery about taking it up that much. So what I normally do is I dial it up to 3 amps, and then I'm going to measure the voltage. Okay, so what I'm going to do here, I'm going to turn our voltmeter on. Okay, and I'm going to dial this up to 3 amps. Okay, so I'm not sure whether you can see this, but okay. Okay, there we go. It's right on 3. Okay, and right now we have 6.72 volts. Okay, so now you got to do the math for that, right? So again, that's just Ohm's law. So you got 6.7 divided by 3 amps. So that's going to give you an armature resistance of a little over 2 ohms. Okay, so you'll need that to do some of your calculations after. Okay, so now what I'm going to do is I'm going to set up for the second part, and we'll get going with that. Okay. Okay, so this is the second part of lab number 1. So what we're doing here is we are applying a field voltage with the variac I showed you earlier, and right now I've got 70 volts DC on the field and about 320 milliamps of current on the field. Okay, so again, we didn't use the DC drive to provide the field voltage because it's a fixed voltage, and we're going to do 2 different steps of field voltage. Okay, so the first step is going to be our 70 volts, and the second step will be 100 volts. Okay, so we're going to make 4 different tables. Okay, so we're going to have the field voltage of 70 volts with the motor unloaded, and then with it loaded. And then we're going to do 100 volts with it loaded and without it loaded. Okay, so, and then what we're going to do is we're going to go up in 20 volt increments of armature, and we're going to read our speed and I will read the DC current as well. So the readings I'm going to call out are RPM and IA, armature current. Okay, and then the other readings we should know, right? So again, for the first two sets of readings, the field is 70 volts, and the armature voltage is going up in steps of 20. Okay, so let's get started then. So we're going to deal this up to okay, so at 20 volts, okay, we have 460 RPM and 350 milliamps of armature current. Okay, so 40 volts, 976 RPM, and we're at about 420 milliamps of current. Okay, 60 volts. Okay, 60 volts. It's 1491 RPM and 500 milliamps. Okay, and then 80 volts is 2034 RPM and 600 milliamps. Okay, so now what I'm going to do is I'm going to apply a field or a load on the motor, and I'm going to go in reverse. Okay, and there's a reason I do this. Anytime you are operating a motor under load, you shouldn't make drastic changes because the amount of current draw really spikes. Okay, so if you've got like high RPMs and you start changing the load, it's able to handle it a lot better than if you're at a very low voltage and you're risking stalling the motor and possibly doing damage to different components, because at a stall you're like really drawing a lot of current, right? So let's add our load. Okay, so actually I have 3 amps of current going into the AC motor to provide the brake. And so right now, again, we're at 80 volts, and we're still doing the 70 volts of field voltage, okay? So at 80 volts, we're at 2019 RPM, and we're at just about 1.2 amps of current. Okay, so we'll dial this down. Again, we'll go slow so we're not causing a lot of current spiking. Okay, there's 60 volts, 1458 RPM, and 1.2 amps. Okay, now things aren't changing. Like for the RPMs, they should be the same at the same voltage. The current should be the same, right? Because, or sorry, well, the current stays constant with the constant load, right? Because that's what develops the torque. The more load you have, the more torque required, right? And so the current goes up, right? And again, if you look at the document that you were supposed to have looked at, you'll see the equations and how all that stuff factors in. But then the speed should be the same, right? Now I'm using analog meters, so Again, the speed might be off just a tad because the readings I'm making are just maybe not exactly where they were on the previous set of readings. I'm trying to do the best though. Okay, let's go down to 40. Okay, there's 40 volts. We went up to 1.4 amps and 918 RPM. Right, so the current is going up a bit because now we're going at a lower RPM, and the inertia load of the motor and that weight of the rotors and stuff like that are becoming more of a factor. So that's why, like, sometimes, you know, these things are supposed to be linear, but they're only linear within a certain range of voltages, because when you start reaching, like, getting into saturation regions, well, things change. It's not going to be linear anymore. Or when you get at a really low speed, you're going to have the inertia loads becoming more and more prevalent compared to the actual just regular speed and drive of the motor. Okay, so let's go down to 20. Okay, there's 20. So that's 382 RPM and 2.32 amps of current. Again, the current's gone up because now the inertia is so much more prevalent. And I'm going to dial this back up again just to get a little of the current off of there, because you don't want to start making changes to things when you've got like high current flow through your motor. Okay, so now what I'm going to do is I'm going to take the load off. I'm going to change the field voltage from 70 to 100 now. Now this is going to give you a significant increase in speed, right? Okay, and now I'll dial this back down to 20. Okay, so again with the higher field. Okay, sorry, I had that backwards. Okay, so with the more field voltage, the slower the speed, right? With the less field voltage, you have higher speeds, okay? Sorry, yes, I said that backwards. Okay, so the field voltage is 100 volts, and the field current is 425 milliamps, okay? And so right now we have no load. So this is our third table, so field voltage 100 volts, no load. So we're at 20 volts. Our RPM is 408. And our armature current is about 400 milliamps. Okay, we'll dial it up to 40. Okay, 40 volts. 870 RPM, about 490 milliamps of current. Okay, 60 volts, 1330 RPM, 520 milliamps. And 80 volts, we have 690 milliamps. and 1807 RPM. Okay, and now I'm going to apply the load. And again, I'm using the same load. It's 3 amps of current there. Okay, and now we're going to work backwards. So it's 1797 RPM and 1.17 amps of current. Okay. We have 60 volts. We have 1288 RPM and 1.2 amps. Okay, 40 volts, 833 RPM, 1.35 amps. And then 20 volts, 341 RPM, and 2.2 amps. Okay, so I'm going to remove the load here, just to make it a little easier on the system here. Okay, so there we go. So we've got 4 sets of data. And these are supposed to be, right, a linear progression, right? From as you increase the armature voltage, the speed increases. And it should be linear, right? Like I say, there are some non-linearities on the 2 different ends of the spectrum where like inertia is a factor, and then it creates non-linearities, and then on the other end, saturation creates non-linearities, right? So the whole purpose of the lab, right, was to figure out our motor constant. And motor constant is basically the slope of this line, right? It's in kilo RPM per volt. So the slope of your line should give you your motor constant. And then you should be able to go through the calculations as we laid out in the introduction part and in the document that supports lab number 1, and you should be able to calculate it. So you should have a couple different measures on what your constant is, and they should all be pretty close to being the same. Okay, so then one of the things, the last thing we do is we do a prediction. Okay, so we did like 20, 40, 60, 80. So what we're going to do is with 100 volts of field, because that's what I've got it set at right now, you're going to predict what it is at 70 volts with no load. Okay, because I'm not going to use a load. Okay, so really it's just a linear thing. So you could just take the halfway point in between 60 and 80 and you should be bang on. You should also be able to calculate it with our equations, right? The speed equals VA minus IARA over K phi something. Well, you do the reading. Okay? And you should be able to calculate the speed. Okay, so let's dial this up to 70 and we'll make the readings, but then we want you to calculate and compare with what we actually measure here. So we're going to dial this up to 70. Okay, there's 70. And you should be able to predict the speed, right? So the speed right now is 1575 RPM. So you do your calculations. Do it from the graph. You can do it multiple ways and prove that this should be the speed that we're measuring. Okay? So there we go. That's all the readings we do for lab number 1. And we'll see you in 2 weeks for lab number 2. Okay?